I hope everyone's doing well. Thank you for joining me for this video where we are looking at the reaction at alpha carbon or the alpha hydrogen. Why is there an or? Because this right here is your alpha carbon. The hydrogen attached to it is your alpha hydrogen. And it's important. This right here is your carbonyl group. The carbonyl group and the carbon next to it is called your alpha carbon. Then the hydrogen on that alpha carbon is called your alpha hydrogen. This hydrogen here is acidic with regards to organic compounds. It's acidic and it can be plucked away and then a reaction can occur over there. You can generate a carbon-carbon bond, and that would be the essence of what you would be doing here. You're trying to add a carbon atom over here which would represent part of another molecule, and you've generated a carbon-carbon bond. The reason why this hydrogen is acidic is because if you look at the carbonyl group, this oxygen is sucking electrons towards it because it's electronegative. It makes it partially negatively charged. The carbon has electron density pulled away from it, becomes partially positively charged. The carbon attached to it, your alpha carbon, and then the hydrogen, the electron density is still being sucked away by the oxygen, so it makes this acidic and it can be deprotonated and a reaction can occur. By virtue of that carbonyl group and the electronegative oxygen, it makes this hydrogen acidic. To carry out this reaction, you need a strong base, and your strong base would be LDA. It stands for lithium diisopropyl amide. It's strong enough to pluck off that alpha hydrogen. So this is what our essence of the reaction would be. Our focus is here at the alpha hydrogen, which resides on the alpha carbon. These R's represent rest of molecule, which means they're really carbon atoms to which other items are added, rest of molecules. But the focus here is on this alpha hydrogen. When I react this in the presence of a strong base, lithium diisopropyl amide in tetrahydrofuran, it's your medium, your solution medium, then you will pluck out that hydrogen, and what you will end up with is this RC and then R and then this. The hydrogen has been plucked off, so you've created a carbanion, a negatively charged carbon, and then you have exactly this. Let's show you everything here with regards to the electrons. These are your lone pair of electrons, and this can resonate between two structures, which can make it stable because the negative charge can be spread around the molecule. You can spread it in the following way, and these would be your two resonance structures. You have RC and then R. You have this carbon, then you have a double bond here, and then you have the oxygen, and the negative charge comes over here, and then this. These are your two resonance structures. You have a negative either on the carbon or a negative on the oxygen. Notice the electrons, 2 electrons here, 4 here, 0 electrons here, and 6 here, but the net effect is still the same. Here's your negative, and you can resonate. The fact that you have resonance structures, it stabilizes that negative charge and it allows the reaction to proceed because these intermediate items are stabilized. When you react this, now you've generated this negatively charged, the reaction will occur right over here at the alpha carbon. And then what will happen is we will react it with the RX. What's RX? A alkyl group, a carbon atom attached to a halogen. And you know this right here can act like a nucleophile. It's negatively charged. It will seek out something like this because it's going to again have the effect that the halogen bonded to a carbon, this is more electronegative, this is more electropositive. So this is an area where a reaction can seek, or where a nucleophile can seek, and it can pluck it off and pull the halogen away. What your end result will be is this R group will attach to this carbon, and your end result is this RC and this R. This is what I've added, and then R, and then you have C double bond O, and then R plus what would we have? HX. This hydrogen has added to this X. What does X represent here? A halogen like chlorine, bromine, preferably chlorine or bromine. And X here would normally be chlorine or bromine. And that's what it is. We've generated a carbon-carbon bond. Remember, R represents the rest of the molecule, where the R, the actual item which is attached, is a carbon atom to which other things are attached. So you have generated here a carbon-carbon bond by means of this, using a strong base, plucking off an alpha acidic hydrogen. And we are done.